Okay, so and so we've already kind of talked about this a little bit. The different types of Riemann sums. You can have so we've got the same curve here three times. It's just a line. Okay, but if you did if it's hitting through 0, 0, and you're doing left ones, so this one would be seriously. Most people will call it an L4. So that's an L4 where all of the rectangles are hitting at a left endpoint. See that? Left, left, left. There's the right. The right's lower in this case. All right. Now the left there kind of smushed, and I don't even have anything. That thing got smushed down into the ground. So the left one's odd. But then the right four has is like what we saw a minute ago. So right, 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 right. Okay. Then, but also you could do what's called a midpoint Riemann sum of four, where you hit at the midpoint of the rectangle. So if this went from 0 to 1, that has it half. That's 1.5. That's 2.5. That's 3. Over here, the rectangle is hitting at 0, 1, 2, 3. Right here, the rectangle is hitting at 1, 2, 3, 4. But either way, there's four of them. Okay, in each instance. Okay, which one's better? You may make an argument that it looks like the midpoint one would be better in this situation. Yeah, but they're all just approximations. So there we go. Now, okay, here we go. This gets a little technical. All right. If you're going from A to B, like right here, we'll look at this one. All right. And it's continuous and it's a greater than 0, like this is the whole time, then A to B can be partitioned, broken into however many that you choose. Okay. In this case, we chose 4, and it looks like they were going from 1 to. It looks like they're one wide, but it didn't say that. It just said from A to B. So if you wanted to find out what each of these changes in x would be if they're going to be the same, then and they call that the change in x. All right, delta x. So delta x would be, I just need to find out how far that is and then divide by how many I'm wanting. All right, so it'd be b minus a over n. You see that right here. Okay, so b minus a over n is going to be the width of each of those rectangles. I mean, in this case, it's easy to see. If I go from 0 to 4, right, if that is indeed 4, then 4 minus 0 is 4, divided by 4 is 1. They're all 1. Okay, but you could do that for anything, even if it's crazy fractions or whatever. Okay, so b minus a over n. All right, so then the definite integral, the area. So this is another way of thinking about this is area. I know it says that at the very beginning, but this is area, would be adding up these rectangles, okay, from 1 to n, whatever that is, where this is the width of the rectangle, this is the length. So C of K, K is telling you, okay, I'm going from the first one would be 1 K of 1, right? 2, 3, 4, right? So I'm finding out the x values here are all going to be based on that k. All right, we'll talk more about that later. But then, wouldn't it be so much better if you just added up infinite number of rectangles? Okay, so here I had 4, but wouldn't it be better if that n went to infinity and you then would have the area, not an approximation, you would have the exact area. Okay, so this is still an approximation here when you add up the rectangles, but not if you send the rectangles to infinity. Okay, all right, now let's talk a little bit more about that. So it says draw a rough graph, use the formula b minus a over n to determine the lengths that you want to use. Okay, and then compute the x coordinates of the rectangles on either left or right end. You could do midpoint as well. Compute the area of each rectangle. Okay, and then add them up. Okay, that's what we're doing. All right, now in example 3, though, it says find that area underneath this curve using geometry. So it's not, so now all of a sudden we're just abandoned. We're not doing the rectangle thing. It says find it exactly using geometry. Okay, so in other words, I'm about to find the exact integral, the integral from 0 to 5 of f of x dx. Okay, that's proper notation here. All right, but I can find it not by using rectangles now, which is kind of weird that we've abandoned that just for a moment, but I can do some geometry, right? And this area right here is a trapezoid, all right? And it's sitting on its side, Okay, so this the area formula for a trapezoid, you're going to have to know this. The area formula for a trapezoid is 1/2 the height of the trapezoid, and then the two bases added together. And what's up with that is it's just two triangles that have the same height, and they have different bases. So this would be like base 1. This would be like base 2. The height is here. This trapezoid is sitting on its height. All right. And so, but we know these amounts. All right. So it's 1/2. The height is 5. All right. Base 1 is 1. Base 2 is, they just went up by halves, right? So base 2 is actually 3.5. Okay. So how you want to deal with that? Let's just go. All right, so I got half of 2, 2.5. So I got 2.5 times 4.5. Okay, and if I'm just gonna go ahead and look at the key. So 2.5 times is 11.25. Okay, now and squared units, but we're good. And Gene when doing that just did everything with improper fractions. All right, to get the 11.25. All right, so that's it for number 3.